Acid deposition can reach the earth in various wet forms, including rain, snow, and fog, or it may settle as dry particles. The most familiar form, acid rain, is commonly used as the term for all types of acid deposition. Certain chemical species in the atmosphere, chiefly sulfur and nitrogen oxide pollutants, lead to the formation of acid rain. Since both natural and anthropogenic sources of these pollutants exist, atmospheric change has existed long before modern industrial society. However, the rate of change has been greatly increased by human activity over the last few centuries. The global threat of acid rain exists because atmospheric pollutants are capable of traveling long distances before acidic deposition may occur. Because of the potential long-range implications, acid deposition may present itself as a problem in other areas without cost or liability to the polluter. Regions in the immediate vicinity of major pollution sources may also face particularly destructive effects. Here is a diagram of typical acid rainfall in the United States. To begin our discussion of acid rain, we will briefly explore the basic concept behind the topic of acidity.
The pH scale is a logarithmic relation frequently used to represent the hydrogen ion concentration of an aqueous solution. Neutral solutions are designated a pH of 7. A pH below 7 is said to be acidic, while a pH greater than 7 is termed basic or alkaline. Each unit on the pH scale represents a 10-fold change in acidity or alkalinity. For example, lemon juice with a pH near 2 would have approximately 10 times the acidity of a cola beverage with a pH of 3. The pH of some other familiar products are as shown. Distilled water has a pH of 7, but we are rarely dealing with this form. Pure unpolluted rain is naturally acidic, with a pH of around 5.6. Even under normal conditions, carbon dioxide from the atmosphere dissolves in water. The product of this process is a dilute solution of weak carbonic acid. Acid rain is usually described as having a pH of below 5. In some extreme cases, acid rain with a pH as low as 2.1 has been recorded. Most living organisms cannot survive in waters with pH much below 5.0. This is due to aluminum ion toxicity, which is leached out of soil and rocks at a low pH. Despite current pollution regulations, the pH of rain in the northeastern United States still averages between 4.1 and 4.3.
As mentioned previously, the two main contributors to acid rain are sulfur and nitrogen oxides. These compounds are given the generic chemical formulas SOX and NOx. These pollutants rapidly oxidize in air under several different pathways. The sulfur and nitrogen oxides may then combine with water to form aqueous solutions of sulfuric and nitric acids, respectively. Some natural rainwater acidity is crucial to the weathering of rocks and minerals, which drive Earth's long-term geochemical cycles. However, increasing acidity by sulfuric and nitric acids pose significant problems. We will look at these effects after viewing the major sources of sulfur and nitrogen oxides.
Natural sources of sulfur in the atmosphere come from three major sources: volcanic activity, the bacterial decay of organic matter, and ocean emissions. Approximately 10 to 20 million tons of sulfur may be emitted in the form of sulfur dioxide every 10 to 100 years due to major volcanic eruptions. The eruption of Mount Pinatubo in the Philippines in June 1991 is one such example. Another 20 million tons are released every year by small volcanic vents. Bioorganic emissions from land and shallow water bodies may account for 30 million tons per year. The oceans annually emit approximately 40 million tons of sulfur in the form of dimethyl sulfide. Sulfur oxides are responsible for the majority of acid rain in heavily industrialized areas. Anthropogenic sources may double total worldwide sulfur emissions. Coal is composed of mainly carbon, but can contain up to 6% sulfur. Coal-burning power plants, ore smelting, industrial fuel consumption, and transportation release a total of approximately 100 million tons of sulfur into the atmosphere each year. The United States alone is responsible for releasing about 15 million tons of sulfur per year.
Nitrogen is the most abundant gas in Earth's atmosphere. It is also an important component of plants and animals. Natural sources of nitrogen compounds in the atmosphere include soil emissions from bacterial decomposition, lightning, and combustion of biomass. Together, these sources represent approximately 20 million tons of nitrogen each year. Another 20 million tons of nitrogen are added to the atmosphere by combustion of fossil fuels. 10 million tons worldwide are the result of field burning. and the application of fertilizers contributes another 20 million tons of nitrogen into the Earth's soil. Whereas sulfur emissions are the main source of acid rain in industrial areas and areas that rely upon coal to generate electricity, nitrogen oxides are more prevalent in cities such as Los Angeles, where the majority of air pollution is from automobiles. Our mining practices have greatly accelerated the amount of sulfur and nitrogen released into the atmosphere, while the Earth's recycling system continues to operate at a much slower timescale. Earth's natural processes of sediment uplift, weathering, volcanism, and deposition operate over a timescale of millions of years. However, if recent consumption trends continue, we can expect to exhaust the reserves of many common fossil fuels within a period of tens or hundreds of years.
Some direct effects of acid rain are hard to investigate because there are so many variables to consider, while other effects are more conspicuous. We can confirm, however, that acid rain adds an additional stress on natural ecosystems. Some of the effects include the leaching of toxic metals such as mercury, aluminum, and lead from rocks and soil, reduced agricultural crop yield, damage to forests and decreased productivity, acidification of lakes and other water sources, reduced species diversity in acidified waters, increased mortality rate of eggs, larvae, and young fish, the corrosion of metals including zinc, copper, steel, and copper alloys, paint and rubber damage, and disintegration of marble or limestone buildings and monuments. This last process occurs when sulfuric acid attacks calcium carbonate, composing marble or limestone, to form calcium sulfate, a crumbly, slightly soluble material. One of the ways in which aluminum ions are leached from rocks and soil is demonstrated by the following reaction.
There are three approaches to combating acid rain. They include reducing pollutant emissions, dispersing the emissions to a greater degree, and compensating for increased acidity at the site of deposition. To reduce pollutant emissions, fuels low in sulfur may be used, or sulfur can be removed from those fuels with higher sulfur content. The emissions from coal power plants and industrial smokestacks can also be scrubbed. Scrubbers function by oxidizing sulfur dioxide in the exhaust stream into sulfate, which is soluble and can be washed out of emissions. Sulfur dioxide can be removed from emissions when coal and oil are combusted by injecting powdered limestone directly into the furnaces. Lakes that are most susceptible to acid rain are those with low concentrations of basic ions to buffer the pH changes. Limestone rocks can help neutralize excess acid in lakes. Acid rain is clearly a problem with considerable health and economic consequences. While the human influence on this phenomenon is unmistakable, the ultimate results of our current actions are yet unknown. Even though stricter regulations have greatly reduced sulfur and nitrogen oxide emissions in recent years, acid rain continues to be a serious problem. Perhaps the best solution will involve developing large-scale clean energy sources such as wind and solar power. New political and economic strategies, such as tradable pollution credits, may also prove to be an effective combatant. Acid rain is just one of the major pollution problems with global implications. From here, we will examine the familiar topics of global warming and finally stratospheric ozone depletion.